Okay, let's finish up the last 4 problems of the sample test. This one wants us to find the best linear approximation. Well, if I remember correctly, our linear approximation looks something like f at that A plus f prime at that A x minus A. So let's use what we have here. All right, f of x is 1 plus x to the 1/2. So if we evaluate that at 8, it's 9 to the 1/2, which is 3, right? So let's take the derivative. That'll be 1/2, 1 plus x to the negative 1/2. The derivative of the inside is just 1. Let's evaluate the derivative at 8. It's 1 over 2. And this thing is really the square root of 1 plus 8. So this is 9 square root of 9 is 3. 3 times 2 should be 1 over 6. All right. So the linear approximation is going to be it'll be 3, because that's what we got there, plus 1/6 times x minus 8. So now we have to just simplify. 1/6 times x minus 8 over 6, which is 4 over 3. 3 over 3, 3 is 9 over 3, isn't it? So 9 over 3 minus 4 over 3 is 5 over 3. So this is a line, which is what we expect, right? Linear approximation is the line. So this right here is our best linear approximation at x equals 8. All right. Next, here's one of our related rates problems. All right, a cup full of olive oil falls on the floor, forming a circular puddle. Its radius r, right, is increasing at a constant rate of 0.4 centimeters per second. What is the rate in the increase of the area of the olive oil when the circumference is this? So here's my picture. What do we want to find? We want to find dA dt when the circumference equals 20 pi. What do we know? We know dr dt, and it's increasing, so it's a positive. So let's see, we're going to take the equation for the area of that circle, pi r squared. Let's take the derivative with respect to time. dA dt equals 2 pi r dr dt. Well, the only thing we don't know is r, but they gave us a circumference, which is equal to 20 pi, right? And the circumference is 2 pi r. So if I divide by 2 pi, I am going to be finding this when the r is equal to 10. That was the last piece of information. All right, so 2 pi r dr dt, which is 0.4 centimeters per second, right? So if I multiply this, I'm going to leave the pi in the answer. That's what he did. So 20 pi divided by 0.4 is 8 pi. And this is change in area, so it has to be centimeters squared per second. All right? When I plugged in the pi, I ended up with something like, all right? So that one's pretty straightforward. Let's see, make sure we can do that guy. All right, now, a rectangular sheet of paper is to contain a black triangle and a white border. So let's draw that. First, we're going to draw our black triangle. His area is 32 square inches, right? He's going to have a length and a width. And then the white border has 2 inches on top. 2 inches on top, but only 1 inch on the side. So I'm trying to make that look. All right, so in here, this is 2. This is 2. this is 1, and this is 1, isn't it? Now it says write the formula that can be minimized. We want to minimize area, right? It says least amount of paper. So we want to minimize the area. Now area of the whole thing is length times width, right? But our length times our width isn't just the paper. I mean the black paper, it's the whole thing. So we would end up with something that looks like this, right? We have our length plus these 2 on the sides. Well, when I look at his answers, what he did was he actually called the width here the L and the length here the width. So let's not worry about it. So this thing here has 2, 4 added to it, right? Length plus 4. The width has 2 more added to it. But we have to get rid of one of those variables. So we go back to what they told us about length times width has to equal 32. So let's solve for width. We're dividing by length. It's 32 over L. So here is the equation we are going to minimize right here. So now it's a matter of plugging and chugging. So let's multiply this out. First is just 32. Outer is 2L. Inner is 4 times 32, which is 128, and I'm going to write L to the minus 1 because I'm going to differentiate it shortly, plus 8, right? So this equals, if I put these together, 32 plus 8 is 40, plus 2L plus 128, L minus 1. So in order to minimize, I have to take the derivative. The first term goes away. I have 2 minus 128L to the negative 2, right? So this really equals 2 minus 128 over L squared. I'll set it equal to 0. So I'm going to move the 128 over L over, this is what we get. So 2L squared equals 128, L squared equals 64, L has to equal 8. Now keep in mind what L was there. So if L's 8, this is of the original black paper, right? W has to be 32 over 8, which is 4. And then you come over here, length plus 4 is 12 times 4 plus 2 is 6. That, thank goodness, is the answer he got. Now, you could have done it with the L and the W in the other spots, because it looks like the original black paper was actually kind of set up in this portrait style, wasn't it? And that's okay. We should get to the same final answer. As long as you define the variables where he can tell what you defined, then the answer will make sense. You just have to kind of put some words around it. All right? All right. This one says, see if the following limit exists. Limit of x going to 0 of x ln of x. Well, what you want to do is set this up because this is just 0 times infinity, I think. So we do need to write this something in L'Hopital's rule. So this is what it looks like, right? I just took this, moved it to the denominator. So this would be negative infinity over infinity. We got to do L'Hopital's rule. So the derivative of the top is 1 over x. The derivative of the bottom, which is x to the minus 1, is minus 1 over x squared. Well, let's look at that. Let's rewrite this for a second, not as a quotient of fractions. So it's the numerator multiplied by the reciprocal of the denominator, right? Which now equals negative x, doesn't it? Now, we can take the limit as x approaches 0 from the positive side of negative x, and we get 0. Okay? So anytime they give you one of these, try to write it in the quotient so we can use L'Hopital's rule. Okay? I think that's happened more than once. All right, let's keep going. Finally, we have a function for this interval. Now notice this is a closed interval. When you have a closed interval and you want to maximize, you look at the critical points and you look at these edges, don't you, when it's closed. So we're going to take this and take the derivative of it. So I'm going to bring down to negative 3x plus 4. So to find the critical points, I set it equal to 0. 4 equals 3x, x equals 4/3. All right, well now we have to evaluate the original function, right? So if I go back and look at the original function at 4/3, I end up with something like this, right? Then I need to check these edges. Oh, I know what I did. Well, this was 4/3 is like 1.33, right? To make sure it was a maximum, I checked on either side of it. I went a little lower and I went a little higher, and I found out that 6.4 was here and 6.25. So I did show that this critical point was a maximum. But for us to maximize the function, we do have to check at the edges. So P of 0 and P of 4. So P of 0 gave us 15, P of 4 gave us 7. So this is indeed a max of this function over this closed interval. The key there is you have to check. When it's a closed interval, you have to check each of those edges. On the other hand, I think if it's an open interval, they say something like, as you approach these numbers, if these are, let's say, maximums over what we calculated, then we're going to say no global maximum exists, right? If it exists as we approach the open interval edges, no global max exists. Over here, we have to check the edges. Okay? Now, so that's the last 4 questions. And I believe what he wanted here, put a box for, all right, maximize it. So when x is 4/3, and if I change my answer to fractions, this is the point of maximum value for that function. So take a look at these and let me know if you have any questions. All right, thanks.